So far, we have talked about cyclic groups and normal subgroups, some properties of cyclic groups and normal subgroups. Or also some criteria when a subgroup is normal, like if the index of the subgroup is 2, then it has to be normal. So now from now on I will talk about homomorphism between groups. Homomorphism between groups. So basically, it's a map between two groups, say G and H, such that so you have a binary operation on G. Let's call it star 1, and you have a binary operation on H. Let's call it star 2. So you have a map. Let's call it F. So F is said to be a homomorphism if uh, if you take any two element from the group G, you can do this operation, and you can send it to some element, and that should be equal to first you send A, and also you send B, and then you take the operation of each. So basically, it's called structure preserving map. Structure preserving map. So it basically preserves the structures of both domain. This is called the domain and codomain. Right. So some let's see some properties and some examples. So firstly, so from now on, I will not denote it star 1 and star 2. Like I will just write it as f of AB is FA. It should be understood from the context that here this operation is happening inside the domain, and here this operation is happening inside the codomain. So let's see some properties. Firstly, suppose you have a homomorphism between two groups, and we know always that there is at least one element precisely the identity of the group. And so let's see what a homomorphism does to an identity element. So if you take, let's call this identity to be 1G. So you have identity here and you have some element here. So now the question is, where does this identity go? So what you can do is, so you can write this identity as identity times identity, right? If I denote the operation to be star 1. And by property of homomorphism, you get this, right? And now you can cancel them. Or by cancelling, I mean you can multiply with its inverse. So you get this has to be the identity of H. So identity element has to go to the identity of the codomain if it's a homomorphism. So it's a first property. Now let's see what's the second property. Again, from there it follows. If you have, say, an element A and you have A inverse, it has to be like this, which is f of identity of the group G, which is this. So it means f of A inverse is fa whole inverse, right? Because you have fa, you have fa inverse, and product of them is the identity of the codomain. So that's the second important property. So now let's see some third property. So then again it's easy. F of a power n is f of a whole power n for all n greater than 0. That just follows from the definition. Another one is if from, say, G to G, and I'm precisely taking any element goes to its inverse, is a homomorphism if and only if G is abelian, right? That's very easy because why? Because this this holds for all AB in G if and only if G is abelian. Right? Precisely. This is same as saying the inverse map is homomorphism if and only if G is abelian. So these are some properties. Now let's see some basic example. One is always there between any two group if you take any element of the Z and send it to the identity. So this is called the trivial homomorphism. It's always there. There's nothing interesting about it because you are taking you are sending every element to the identity, but it's still a homomorphism and it's called trivial homomorphism. Also, we have again a very trivial case. They are sending each element to this. This is called identity homomorphism. Right? Again, pretty easy. Now, the third example you can think of is you can take say GLNR and send it to uh, or minus 0 with respect to multiplication. Any matrix goes to its determinant. And you know determinant of AB is determinant A times determinant B. This is precisely saying that determinant is a homomorphism between these two groups. Right? So these are some examples. Also you can take say if order of G is odd, then consider this map any G to G square. Is it a homomorphism? Another question. Well, again, the answer is if, or maybe you should think about it. So think about it. And let me state another definition. So you have suppose this is a homomorphism. Now you know what's a homomorphism. So this is a homomorphism if it is also one to one. That means injective. Injective is called monomorphism. If it is also onto or surjective, it's called epimorphism. So homomorphism that is injective is called mono, and homomorphism which is surjective it's called an epi. And if it is both monomorphism and epimorphism, then it's called an isomorphism. So basically we have a homomorphism that is also bijection. It's called an isomorphism. So and this concept of isomorphism is very very important in group theory. We'll see why and how it's later. Yeah. So let's see some more examples. So for example, you can take Z mod 3 to Z mod 3 and you have a map by say the zero element has to go to the zero element. The one element has to go to like you can send it to anywhere because there's no restriction on one. So I am sending it to two. Otherwise, if you send one to one, it will automatically force you to send two to two, right? So and then what will be two? So you know f of two is 2 times f of 1 because property homomorphism. So this is 2 times 2 bar, which is 4 bar, which is 1 bar. So this is first of all you can see f is 1 1 on 2 and homomorphism. So f is an isomorphism. Iso. Right? And also there is the identity map is always an isomorphism. So Z3 is isomorphic to itself, but the isomorphism may not be unique because you are getting another isomorphism here. You already have the identity here, but apart from identity, we are also getting another isomorphism. And in fact, uh, let me make a note. If G is a cyclic group, then you have a homomorphism here is uniquely determined by its value on G. So basically, if you know the value of f at the generator of the good domain, it's enough. And again, the reason is simple because any element of the group looks like some power of G, right? So if you know what f of G does, you also know what is f of any G power n does because that is just f of G power n. So if you know the value of f of G, that is enough. So yeah. And moreover, so here G is cyclic, F is a homomorphism, so image of F is also cyclic. That is obvious because it is generated by F of G. Because any element would look like some power of F of G. So yeah, that's a basic thing to note. Now let's see what we can we talk about something more. So we have this. Oh yeah, let me now define. So what is image of F? I've not defined it. So it's basically the range of F, meaning f of x, where x is in G. So that is precisely the meaning of image. And also we have the notion of kernel of f. By shorthand, I will denote it by k of f. So these are all elements of the domain that f sends to the identity of the codomain. So first thing to verify, uh, k of f is a subgroup of domain. Second thing to verify, k of f is a normal subgroup of G. Third thing to verify, image of F is a subgroup of H. Fourth thing to verify, image of F is not a normal subgroup. And so naturally the question is when it is a normal subgroup. Okay. So these are pretty, and all of these are really easy. I'm not, so it's just check. These are all really easy. And so now let me define this proposition, which is important. So it goes like if from G to H is monomorphism, if and only if kernel of F is precisely the identity. So it's enough to look at the kernel. You don't have to look at all the values of F. If you know the kernel is singleton, you know that the map is injective. So let's see. Again, it's really easy. The proof is just unraveling the definition of what do you mean by an injective map. So let fx equals to fy implies x equal to y for all xy. So we're assuming f is injective. And if a is in kernel, then you know f of a is identity of h, but that is again f of g. And because f is injective, you get this. So kernel is precisely, because a was arbitrary, so kernel is precisely the identity. And also if kernel is identity, then say you have f of x same as f of y. So this means f of x inverse y is identity of h, which means x inverse y is in kernel, but the kernel is just identity. So you get x equals to y. So again, it's really an easy proof, but it's really important. We often use this criteria rather than checking the value of f at all the points. So yeah, and now, so far we have come across a few examples, some properties of kernel, which I've left it to check, and also we have seen this important proposition. So let's see what more we can talk about in this setup. So so now we know kernel is a normal subgroup. It's an easy thing to verify. So because kernel is a normal subgroup, we can talk about this quotient group, right? This quotient group makes sense, right? So what is this group basically? You are taking all the elements of G, and if there is an element which is in the kernel of F, you are annihilating that element basically, right? So if you have say some non-trivial element in the group, or I mean non-trivial element in the kernel, let's say X is a non-trivial element in the kernel, and so but in this inside this group that X, if you take the uh, coset representative of that element X, you will get it is just identity. So this means that, so now, so now the question is, what exactly is the structure of the group? Exactly is the structure of the group. So you know you have this. So this is a setup. So you have this homomorphism. I will not write homomorphism again and again, so it should be understood. But yeah, so you are given a homomorphism, and now I am taking this map. Let's call it f tilde. And what does f tilde do? You take g plus kernel of any coset. You send it to f of g. And so now my claim is f tilde is injective, because say if uh, f tilde of g plus kernel f is identity, then you get f of g is identity, but that means g is in the kernel. So g plus kernel f, this coset, or maybe why I'm writing plus, so it's just g kernel f. Yeah. So this same as kernel f, right? Because g is inside the kernel. So you get that g kernel f is precisely the identity element of the quotient group, right? Because this is the identity element of the quotient group. So you get if tilde is always 1 1. So that's an important property. Whenever you have a homomorphism, you can always define another homomorphism by the help of that given homomorphism, which is always injective. So now still the question we have not answered exactly. What exactly is the structure of this group? So we'll come to it in the next video. So that is precisely, in this group is precisely isomorphic to the image of F, and that is called as the first isomorphism theory, and arguably the most important result in basic group theory. We'll use it in several occasions, like almost everywhere we'll use it. So this says that this quotient group is precisely the image of F. By precisely, I mean it's up to isomorphism. I will define an isomorphism between these two groups. So yeah, I will come to it next time, and I will also talk about what are the second and third isomorphism theorems. But that is again Those are basically some application of the first isomorphism theorem. So we will see it in the next time.